Alrighty, my name is Doug. I'm a developer advocate with the Firebase team at Google. Before I was at Google, I was at a startup. What we were doing, we were specifically in the space of mobile application performance monitoring. So what we would do at the startup, we were called Pulse.io. What we were doing is we had Android and iOS SDKs that you would drop into your app, write no code, and it would start measuring the performance of some of the things in your app, like its startup time, in particular the HTTP transactions inside it, and also things like dropped frames. The thing that was maybe the most interesting thing to me was the fact that it automatically measured HTTP transactions, all of them within your app, and you didn't have to write any code for that. So that was a pretty interesting challenge. So making developer tools is kind of hard to make money, and so what we ended up doing is we joined the Firebase team. So what you know today as Firebase Performance Monitoring was actually had its roots in what we built at Pulse.io. Now, as you know, performance monitoring is not something that a lot of companies do, but Android does provide some good tools for measuring performance. So many of you probably have already used systrace. So systrace will collect tons and tons of data to a phone or emulator hooked up to your machine. It does have to be hooked up to your machine. It operates over a fast ADB connection. And it collects tons of data, maybe more data than you want. But you can see what all the threads are doing. You can see how busy the CPUs are. Just a tremendous amount of data. But you probably know that if you use systrace, your app slows to a crawl. You really can't use your app, and it has to be connected to the computer. And so this doesn't make sense if you want to measure the performance of your application as it's deployed on your users' devices. That's kind of more important than the one that's hooked up to your machine sometimes, because you want to know what the end user experience is actually like. So what Firebase Performance Monitoring does is you drop the SDK in, and it starts sending telemetry, measurements and telemetry to the Firebase cloud, and then it will populate a dashboard where you can see the performance of everything going on. And again, the thing that was most interesting to me was the HTTP measurement. So you'll see in the Firebase dashboard, it looks kind of like this. You can see patterns of URLs that are being accessed in your app. This dashboard is actually kind of opinionated, so you'll notice the top 3 items have a little exclamation point on them. That's the console being opinionated, saying, hey, these, I think, are the worst ones. You should look at these first if you have any interest in improving the performance of your app. Now, if you click into one of these, you'll see even more information. So you get to see things like what the average response time was, what the payload size was, whether or not it was successful. So was it a 200 or a 500 response, and so on. So this is a pretty intense amount of data. And bear in mind, it's coming from your users in production as they use your app. So this is all very useful information. And you can also drill down by OS level, by device type, by region of the world. So you can really hone in and find specifics. But again, this is running in production on your user's app, and you don't have to write any code for it. That's kind of the catch, is that you don't have to go hunt down all the HTTP transactions and instrument them yourself. It all happens automatically. So how do you do that? How does an SDK do that? It's kind of an interesting problem to solve. And on top of that, there are several different HTTP libraries. So you could be using Java URLConnection, or Apache HTTP client, or OKHTTP. At the startup, we had to support all of these. These are what our customers were using, so it wasn't just one or the other, it was all 3. Now, interesting thing about these APIs is there's no real good hooks to just grab that data as it's going through. Like, you can't just tell URLConnection as a whole, hey, give me all your data. That would obviously be a kind of a security problem if anyone could just spy on your data with nothing more than an indication saying that I want to. So what can we do here to actually get this data without writing any code? Well, you could modify source code, right? You could have some sort of Android Studio plugin go in and look at all your source code and try to find all the HTTP transactions and rewrite them. That's one way. If you come from a Java background, you probably heard of this thing called the JVM agent. So when you hook an agent up into your JVM program, what it does is it basically lets you intercept all the classes that are being loaded from the program and decide if you want to make changes to them. So you could do some bytecode manipulation in there. But it turns out Android doesn't have an agent. Only JVMs have this. So if you're working on a desktop with an Oracle JVM, then you have an agent. But Android doesn't have an agent. The other thing you could do is modify the bytecode of the compiled JVM classes before you deploy them. So before they go into your APK. So it turns out the first two are not viable. No one would really trust you to modify all the source code of your app. And also, it wouldn't reach into third-party libraries because you don't have the source code for those. All you have is bytecode. Like I said, the JVM agent is not there on Android, so what we'd have to do is do this at build time. We have to get a hold of all the classes after they're compiled, before they go into your app, and make changes to them. Now, what kind of things are we looking for? Well, here's just a sample. This is one of the 3 different APIs and one variant of URLConnection. So all we're doing is newing up a URL, allocating a byte array, opening a connection to it, dumping the input stream into that byte array, and closing the connection. This is pretty standard stuff, just fetching a URL. So this is what we're looking for. This is like the pattern of code that we want to find in bytecode, and then turn that into something that gets measured. So if you know the Android build process, it goes, you take your source files, Java or Kotlin compiler will compile them. The compiler will generate classes and jars. You end up with a ton of classes and a ton of jars, and all those get fed to DX or D8, depending on what kind of build you have. The dexer will take those classes and convert that into DEX code. That DEX code gets then added to your APK after it goes through AAPT. So AAPT will take the manifest and all your code and all of your resources and all of everything that should go into your app and build that final APK. Now, where does bytecode manipulation sit in the middle of all this? Well, it turns out you pretty much have to do it after you have all the classes and jars, but before they get sent to the dexer. Once it gets sent to the dexer, you no longer really have the ability to do simple bytecode manipulation. So all the bytecode stuff has to go in the middle here. But this raises some questions. So where exactly are all the classes? You have to find them. You have to know where they are on disk. And you also have to know how do you hook the build process? Like, you have to get in right at the right moment in time when after all the classes are built, before they go to the dexer. Now, the way I did this at Pulse.io, before we had Gradle, so we actually had to support Gradle and Ant. So those of you who have done Android development for years and years know Ant, which is really like not great build system, but we had to support it. But anyway, both of those build systems, both Gradle and Ant, had a DEX task. And what I ended up doing was I would find the instance of the DEX task, the literal like Java object that did dexing, and I would reach into it with reflection and find the private members inside it that had the list of all of its inputs, so all the jars and all of the directories. So I would read that, the private config from a class file with reflection, and then what I would do is change it to the locations where I would write my modified files. So I would not only take this as inputs to my program, but I would also dynamically change it to point it to another location where I stored everything. Now, this is actually kind of a bad idea. Don't ever do this. Don't reach into private members with reflection unless you're a scrappy startup trying to join Google. Then it's okay. But for the most part, don't do that. That's a really bad idea. We had to do it, but now there's a better way. We don't have to do all this like hacky private reflection member munging like I did before. What we have today with Gradle, now we don't have Ant anymore, that's good. All we work with is Gradle. With Gradle, you have what's called a transform step. So after all of the compilation has happened and all the jars are known, you can register a transform, and that transform can apply changes to the classes and jars before it gets sent to DX and D8. So if you're actually using ProGuard, and I know that modern builds use R8 instead of ProGuard, but ProGuard is actually implemented as a transform step. It's the last transform step. It's the thing that's going to strip out all the code that's not used when it does its analysis. But you can register your own transforms in the middle, and that's how the Firebase Performance Monitoring plugin works. So with my project, I have open source, and there's a link at the end of this. It's not the actual plugin. It's sort of a stripped-down plugin. There are 3 parts to it. There's the Gradle plugin itself, the thing you apply at the top of your file to let it know at build time, I have some work to do. There's also a companion SDK that you build into the app. It's a regular compile dependency. That provides runtime support for what the bytecode manipulation is going to do at build time. And then there's a sample app itself, so you can actually run the app and see how its bytecode gets changed. So the way I've organized it in source control, and this is just so you can visualize what I'm doing, at the project root, I have the app and the library sitting at the same level. Within the libraries, the module, the Gradle, the Android module sits next to the transform plugin. The module and the plugin kind of depend on each other. The plugin is going to do things that are dependent on knowing what the module expects. So I'll say a little bit about that more. But first, let's talk about the Gradle plugin. So the Gradle plugin that performs the transform, you add it to your build just like this. Now, you see the dependency there in yellow. That should look very familiar to you. If it doesn't, you've probably never done Android programming. But if you have seen it, you know that's the one that you add to your build script. That's the Android build tools. Here, we're not adding it to the build script. We're actually using its APIs within this module. So we have to add it as a compile-only dependency. It's compile-only because by the time it gets added to the Gradle, build, it's assuming that the build tools are already added, and we don't have to load them ourselves. It's just provided. So the other thing we have to do to get started is use metainf with a properties file to indicate where the entry point to the transform is, or the plugin is. So there's just an implementation class equals and the name of the class file. That's where Gradle will look to bootstrap your plugin, and you can start registering a transform. So inside that plugin, all we have to do is subclass plugin, and we have an apply method. And this apply method is what gets called when you apply the plugin at the top of your project. It's doing a bunch of things here, but the most important thing is it's finding the Android plugin. So the Android plugin must already be applied to this project before the transform can work. And if it finds the Android plugin, it will register a transform with it. This is our way of hooking into the build. The transform API is now going to say, OK, when it comes time to do transform, after compilation, but before DEX, run this transform. And then the transform itself, all it has to do is subclass transform, which is provided by the Android Gradle build tools. We have to give it a name. Here I'm just giving it the name of the class. And more importantly, we have to tell the transform what it is we want it to work on. So right now I'm telling it I want to work on classes. And I think that's kind of the only thing you can work on right now. In the future, there might be other things like maybe resources. But all I'm doing right now is saying this transform is interested in classes. So after you've compiled, let me know. The other thing we're doing is we're telling it which classes we're interested in. So when we return a value from getScopes, the scopes determines which classes you're going to get fed. In this case, I want all the classes. I want everything from the project itself, the Gradle project. I want everything from all of its sub-projects, so all of the modules, and all of the third-party libraries. I want to see everything, every single class that's going into the build. I'll look for HTTP transactions and rewrite them at the end of the transform. The other thing I'm doing is I'm saying that this is an incremental build. The only reason why I say this is if you write your own transform, please make it incremental. If you don't, you will slow down the build massively, so you need to be able to detect when your dependencies or when your inputs change and only modify the things that have been changed. So the transform method itself, this is where the transform actually begins. So now we're at the point, everything's been compiled, and we're about to go to DEX. So what we're going to do is get a transform invocation. This transform invocation object is, you're going to deal with this a lot if you end up writing a transform. The transform invocation basically looks like this. This is not Kotlin now, this is Java because this is provided by the Android build tools. Basically what it's telling you is all of the inputs that are going into the app. So this is all the classes, all the jars and everything. It's also giving you an output provider. And the output provider tells you if you want to process an input, where should you drop the files. So you can't just drop them anywhere. You have to drop them in the place that the transform is telling you is allocated for your files. And of course, you can say you can find out whether or not this build is an incremental build. So the entire minimal transform looks like this. Take a picture of it, zoom it when you have time. Actually, I'm kidding. Don't look at this code. It's in an open source repo. You can examine it if you want, but it's 200 lines of really boring paperwork. I'll boil it down to this. Basically, iterate each one of the transform inputs that you get. Then for all the jars and all the directories, iterate all those, figure out if they need processing, get the output location. Now we're doing something interesting. We're going to iterate all the class files and all the directories and jars and do the bytecode manipulations. So we have to find all the classes, load them up, figure out what to do with them, and then write them out into the output provider location. So I'm not going to talk about any of this code except for the bytecode manipulation part because that's where the money is, right? So how do you make changes to bytecode? What's the easiest way to do that? Well, there's this library that pretty much all other libraries that do bytecode manipulation use. It's called ASM. I don't know what it stands for, but it's kind of the granddaddy of all other bytecode libraries. So if you work with any other library like AspectJ will do bytecode manipulation, or Kotlin does its own bytecode manipulation, they all use ASM. ASM uses a visitor pattern to deliver the class contents for you. So what you do is you register at the very top level a class visitor. When you tell it what your class visitor is, anytime it sees a class and there's an item of interest in that class, it's going to call you. So visit with no arguments means I've just found a class. It'll tell you when it finds inner and outer classes. It'll tell you when it finds annotations on that class, and so on. Notice that 3 of these are returning other visitors themselves. So the class visitor doesn't get all the information about everything in the class. It's getting top-level information. If you want to go further, you have to return another visitor that will get registered, and it will return more changes. The most important thing here is the method visitor. What a method visitor does is it will get invoked every time a method is found inside your class file. So both static methods and instance methods. When you return a method visitor from that, it's going to get called with even more information. So the name of the method, any annotations on it, the code itself, local variables, method instance variables, and so on and so forth. Basically, this visitor is going to tell you about every single thing that's going on inside the method of some bytecode. So this is where the interesting stuff goes. This is where all the magic happens. So let's visit some bytecode. When we register a visitor, we're going to get notified of bytecode. But before we talk about bytecode, I want to do a little bit of review about the JVM. So if you haven't worked with the JVM, this is like a crash course in how it works generally. If you've worked with the JVM, this should be a good reminder. The JVM itself, for every class that gets loaded into a JVM, there's a constant pool, exactly one constant pool. It has pre-computed values, so strings, numbers, references to methods, and so on and so forth. They're all indexed by position, so you'll see these little #1, #2 numbers all over the place. If you dump a class using Java P, you'll see a string table or a constant pool look like this. So you can see that constant number 5 is a string called onCreate, and constant number 6 is a string that has a method descriptor. So that parenthesis L Android OS bundle, that's basically saying a method that takes one argument, which is a bundle, and returns void. This is like JVM speak for method signatures, and you get good at reading that after a while. Anyway, you can see that when you dump a class, there'll be a bunch of constants in there, and you won't have to deal with the constant numbers yourself. ASM will help you with that, but you should know that that's what's going on. Every method has local variables, so they're similar to registers in a CPU. So if you've done assembly language programming, you'll know that registers hold like temporarily what's in memory. They're indexed by position. For instance methods, 0 is always this. So when you call a method using, and you have this available, this is essentially local variable 0. And they typically map 1-to-1 with Java or Kotlin local. So if you define a local, it'll almost likely end up as a local variable. You can see here's a method. You can see they're listed in reverse order. So at the bottom, there's index 0. That's this, and that's the class that's being worked on, the instance of that class. And you can see that there's other local variables being used in the body of this method. There's the operand stack. So the operand stack, basically what happens is you push values onto the operand stack, then you execute some operation against all the values that have been pushed onto the stack. So what happens is you push, operate on the entire stack, and then pop the result off. I think of it kind of like reverse Polish notation. So if you've ever used a calculator that requires you to put the operands in first, then the operation, it's kind of like this. It's basically a bunch of pushes, operate, pop, and that's it. So if you were to do some addition in Kotlin, say you have 2 local variables, add them together, put them in another local, you would load one integer from a local variable 1. You would load another variable from local integer 2. You would add them both. So that will pop the 2 values off, push the result back on, then you can store that in some other local variable and then pop that off the stack. So after all this is done, the stack will be empty and it'll be waiting for new instructions. Now, understanding how this operand stack is actually key to how the Firebase Performance Monitoring plugin actually does its work. There's also stack frames. So stack frame is created on the stack for each method call. So any static or any instance method, when it gets invoked, the JVM effectively creates a stack frame. All the locals go in there. There's space allocated for the entire operand stack, so it knows the maximum size of the stack and pre-allocates that for you. And then when you return from the function, that whole stack frame gets popped off. So I'll use these terms a little bit during this talk. Just keep them in mind that they do have special meanings in the JVM. Okay, with the JVM crash course out of the way, let's look at some actual bytecode processing. So this class instrumenter is sort of the main of my code that does instrumentation, and there's a method called instrument on it. The input to this is a byte array. This is the bytecode, or this is the contents of a class as a byte array being fed into this method. And you can think of it as having already been read out of a file. I'm not showing that part. That's kind of boring. But the first thing we're going to do is use ASM and create a class reader. Class reader is provided by ASM, and you just feed it the bytes that it's supposed to parse. Now, it's not parsing anything yet. It's just waiting. It's about ready to execute. The other thing we're going to do is create a class writer. A class writer is also provided by ASM. This is effectively a method, or this is a class visitor, and it's going to get visited for all the elements that it's supposed to write out. So if I did nothing else here, I could hook up the class reader to the class writer, and it basically just copies everything from the reader into the writer. But I want to make changes. I don't want to just copy the input to the output. So what I can do is create my own instrumentation visitor. This is a custom class, and I'm going to feed it the class writer. It's wrapping the class writer. I'm decorating it. So what I'm going to do is, instead of having ASM write directly to the class loader, ASM is going to write to me, and then I'm going to write to the class loader. So when I tell the class reader to accept the input, what that's doing is kicking off the whole process. My instrumentation visitor will get called, will get visited for everything in the class, and then I'll dump that byte array back to the output. Okay, so here's what's going on at a high level. We have class bytes. There's an array of bytes for the class file. I'm feeding it into a class reader. It's going through my instrumentation visitor, which is a class visitor. It's invoking the methods on the ASM class writer. It's decorating it, and then the class writer is going to write out the modified bytes. So that's what's happening kind of on a per class basis for every single class in the app. So the instrumentation visitor itself looks like this. Notice that it subclasses class visitor, but it takes a class visitor as input. Again, this is decorating, so I'm decorating the class visitor that's passed as an argument, and I am myself a class visitor. And there's some configuration files that determine how it works. Because this is a class visitor, I can subclass interesting methods on this. So my visit method will get called when the class is first started. I'll know things like the version of the class file, access flags, the class name, signature, and so on. Whenever a method is visited, like I mentioned before, visit method is called for all the methods in the class, and I can get access flags, the name, the description, the signature, and any exceptions that are declared to be thrown. So that visit method, remember, that's the interesting one. That's what's going to get. That's where all the bytecode is going to get delivered. So this is of special interest to me. So when I go to implement this, notice that it returns a method visitor. I am obliged at this point to return a method visitor that will get invoked when all the bytecode is visited. So what I'm going to do is call through to the superclass. The superclass, remember, is my decorated class. So I'm saying, hey, decorated class, give me your method visitor, and I'm going to intercept and write through to it. So what I'm going to do is decorate that as well. So my method visitor decorates the method visitor from the class writer. Now I can do all my interesting work. My method visitor. Now we're getting so close to the bytecode. We're almost there. There's just a lot of scaffolding, right? So there's what this is going to do is subclass advice adapter. Advice adapter is an ASM class that is really good at letting you insert bytecode before or after instructions or replace the instructions together. So this is the thing that's smart about working with bytecode. And what I can do here is override a method called visit method instruction. What this does is this will get called anytime there is a method call within the method that I'm processing. So anytime you'll see invoke virtual or invoke static or invoke interface, all of these instructions are now going to get fed into this class so I can know what methods are being called. Now I'll pause here for a moment and just step back and say, well, what are we trying to do? We're doing bytecode manipulation, but what are we really trying to do? Well, we're trying to find code that looks like this. This is that URL connection code from before. We're looking, in particular, we're looking for that open connection call. That open connection call, to me, signals when an HTTP transaction is about to begin. Everything else is kind of superfluous, but open connection says, hey, HTTP is happening right about now. So what I want to do is find what that bytecode looks like and change it to something else. So if I took this class, say I compiled this method into a class and I dumped it with Java P. So Java P is a command line program that you can use to examine the contents of a class file. I can see that the make request method, it takes no arguments, returns a void, it's public, it's final. There's the local variable stack, so you can see the local variables, which is just like the ones we saw before. And by the way, the code in orange up there is the Kotlin, so you can compare the bytecode to the Kotlin that it came from. So we have a local variable table. We have the code itself. So now we're looking at the bytecode in the method that was compiled. So the first line of Kotlin creates a new URL. You can see the bytecode instructions for that. So it's just calling new, and that #10 is the local it's the constant that describes the URL constructor. I'm not going to go through all of this. Basically, this is what new looks like in bytecode. Then we'll create a new byte array. Again, we're going to call new array to create the new byte array to pass to it. Then we're going to find open connections. So this line of code, the first line of Kotlin here, that aLoad1, that's saying, hey, that URL object, I want to load that onto the stack. I'm interested in calling a method on it. And then invoke virtual will invoke the open connection method on it. So #20 there references open connection with no parameters. That returns a URL connection. You don't have to know that. That's just kind of what it looks like in this case. But this signals when that HTTP transaction is about to start. Then there's another line of Kotlin here that I didn't write into my code. This is actually what Kotlin's doing this to check the null safety of the URL. So what it's saying is, I'm going to call this other static method. It's kind of an internal utility method, and that's going to make sure that URL isn't null, and then throw an exception if it is. And you can see that happen again after the call to get input stream. Kotlin is again injecting a bit of code, making sure that that method isn't returning null. Now, for the purpose of understanding this, we don't need to know what Kotlin is doing in terms of null check. We can effectively cancel that out and pretend it's not there and then squash it all together. So now the most interesting part of the code here is URL.openConnection. So we're loading URL, we're invoking the virtual method on it, and we're storing the result back into a local variable, back into in the con variable. And then we're going to load that con variable, call input stream on it, and then store the result of that back into another local. Okay, so this is where it gets interesting. That open connection is what I'm really, really interested in. So what I want to do here is find that open connection, and I want to change it to something else. This is the manipulation I want to perform. So I want to take that call to open connection and instead call a static method on a class that I provide in my companion library. So remember, there's a companion library that contains some code that was added as a compile dependency. This bytecode manipulation is depending very heavily on that library being there. If it's not, this will obviously error out. You won't be able to run this. But if your library is there, now what we're going to do is pass that URL into the companion library. And what that companion library is going to do is effectively instrument that URL. I'm going to use the decorator pattern again to feed it the URL that was being accessed. I'm going to call open connection on it and pass the connection into this class. And then this class now is basically intercepting all the calls to that URL connection, and we're going to return it back to the caller. Now what happened here is the caller is kind of being duped into using my URL connection. That's not the one that they asked for, but it still looks like a URL connection. It subclasses URL connection. It still looks and feels and performs exactly like that first URL connection. So we're being kind of tricky here. This pattern is more generally described like this. So if you have a method on an object that takes some parameters and returns a result, what we want to do is rewrite that as a static method on a utility class that takes the object itself and all the parameters as additional parameters and returns the same result. We're kind of decorating through a static method call. And that utility class looks, generally speaking, like this. Now notice that the object is no longer being called, is no longer having a method called on it right now. It's being passed, and all the arguments are being proxied through to the utility class. Also, you'll see that the original method is being called inside the utility function. So it's not like we're not calling that method anymore. We're just deferring it to inside this utility function, and it's going to decorate the result, and that decorated result has to be of the same type R as the original. In this class, it's almost likely going to be a subclass or some implementation of an interface. So how do I make this pattern work? I want to write this bytecode that does this tricky little change. There's one weird trick, just one weird trick involved in doing all this. So say we have that line of Kotlin that calls a function on a method and takes some parameters. The bytecode for this is invoke virtual, right? So invoke virtual is going to take A, B, and C that are on the stack. Actually, OBJ, A, B, and C are going to be on the stack at the moment that invoke virtual is called. And then after invoke virtual finishes, everything will get popped off, and the result will go back on the stack. So this is what we're trying to duplicate here. We can't change the values of the stack. Otherwise, we've totally screwed up the host program. Yeah, I just said that. OK. So what we want to do is turn this into an invoke static instead. So if all we really need to do here is change the invoke virtual to an invoke static. Notice that the state of the stack doesn't change. There's still 4 things on the stack before and 1 thing on the stack after. And the types of everything has not changed. So what's going to happen here is almost exactly like the original, except we're still popping 4 items off the stack, and we're making a new frame. But instead of calling the instance method, we're calling our static method, and then we're going to push the result back on the stack. So we're doing this little indirection. It's like a redirection. Instead of the invoke virtual, we'll just call the invoke static. And that's really the one weird trick. This is the only change that the Firebase Performance Monitoring library will make to your code. It's just looking for patterns that describe that method on an object. It just knows all the methods and all the objects that could possibly be of interest to it. And it changes them from an invoke virtual to an invoke static into the companion library. So after we've applied this trick, what does the class look like? Well, all we have to do is remove that invoke virtual and add the invoke static. Now, this still satisfies valid bytecode. Remember, the state of the stack hasn't changed before and after. Just now we're calling a static method instead of calling the virtual method. So how do you do this? In ASM, it's pretty easy. You just add code to that method visitor, or that method instruction visitor, actually. So if you remember that visit method instruction that's getting fed all of the instructions and all of the bytecode that it's going to process, all we have to do in there is check to see if the signature of the method is one we're interested in. So I'm going to check to see, is it coming from a URL class? Is it called OpenConnection? Does it take no arguments and return a URL connection? If all of these criteria are satisfied, we want to change this method. We want to rewrite it. Otherwise, I don't want to change a thing. So all we can do is tell ASM, instead of calling, well, let's look at the else first. If we don't change anything, we just call through to the superclass visit method instruction and change nothing. We just pass the call right through and make no changes. But if the method is interesting to us, we're going to, instead of calling visit method instruction with the exact same stuff, we're going to change it to an invoke static. And we're going to direct it into the class, the method, and the signature that I've chosen to redirect. And that's it. That's all you have to do. So if you were to look at the Firebase Performance Monitoring code, which you can't do right now. I think it'll be open sourced eventually. But if you were to look at it, it's basically all configuration that's looking for these combinations of classes, methods, and signatures. That's all it's doing. It just maps all of these source methods to rewritten methods. Now, the static method itself looks like this. So this is the one that is intercepting the call to the virtual method. What it's going to do is look at that URL. And it's going to say, hey, I want to call OpenConnection on it, just like the caller would have originally. But I want to look at the type. Is it an HTTP type connection? Is it an HTTPS type connection? Well, they're slightly different objects, so I have to do slightly different wrappers. Again, I'll decorate the connection in a decorated URL. And this is going to intercept all the calls to it. If it's not one of those, like if it's a file URL connection or something else, I'm not interested in it. I'm just going to return it unchanged. So if this was going to be an instrumented URL connection, now I have an obligation to subclass URL connection and also override everything in it. I have to override every single method, and at the very least, proxy them through to the decorated class. Now, if I want to make a change, or if I want to do some measurement, this is my opportunity. I can jump in here and say, well, if they request an input stream, so if they call get input stream, that means they're going to start reading bytes from the HTTP connection. I want to know what those bytes are. Well, I don't want to know what they are, but I want to know how many bytes were read, how fast were they read. That's how it's able to instrument all of these HTTP calls and give you the telemetry that you want. Now, I'm not showing everything here. There's like 20 different methods you have to override, and they all have different ways of being used. So again, in the production code, it's basically accounting for every possible combination of every possible series of calls. It's internally maintaining a state of what's happening with that transaction. Okay, so in the end, what happened here? We used ASM to replace interesting method calls with static method calls. We used that redirection trick to take an instance method and instead call a static method. So we looked for invoke virtuals, changed them to invoke statics. We also implemented the static method calls to call through to the original method, but also decorate the result. So we're returning back to the client something other than what they wanted, but still behaves like what they wanted and adds instrumentation. The runtime support for that is provided by the companion library. And we have decorators here. The decorators for all of these methods have to override all the methods. They always have to call through to the original object so they don't change the way they behave, but they internally measure the HTTP transaction behavior. So that's kind of what we went through. When you sum it up, it doesn't seem like very much, but when you get right down to it, there's really, really like gritty bytecode stuff going on using that weird trick. So if you're going to write your own transform, I have some tips. Transforms can be slow for large apps. You will process every single class file in an entire app. That's a lot of processing, so be fast about it. Especially, be sure to implement incremental builds optimally. So the Transform API gives you a way to do that. It's a lot of extra code, but it's worth it. If you're writing something for developers to add, allow the developer to disable it easily. I can't stress this enough. The Firebase Performance Monitoring plugin actually released an update lately that lets you turn it off for debug builds, but turn it on for release builds. That's almost exactly what you want, because debug builds, you don't want to instrument it. You want to instrument your release builds that you send to customers. Don't process classes unnecessary. If you're able to figure out before bytecode manipulation if you want to process that class or not, skip it. Just copy it right through. In particular, you should not transform your companion library classes. So that companion library that you have the developer add into their app, that will become part of the bytecode manipulation that the transform does. You should not process those classes, because if you process those classes, you end up in an infinite loop. You'll process the bytecode that has interesting methods in it, and it will redirect those methods to call back into the static methods. So don't do that. I made that mistake once. It was kind of embarrassing, and I didn't tell anyone about it, but I'm telling you now, don't do that. You should write integration tests against your transform classes. At Pulse.io, when I wrote this all originally, I was obsessive about writing both unit tests and integration tests. I wrote a slew of code that would instrument a class, load the class, call its method, make sure it was doing everything it was supposed to do. My logic here was that I am effectively writing a transform that is going to modify our client's code, potentially many hundreds of lines of it. We cannot afford to screw up on this, right? If you screw up and you ship something that doesn't work or breaks in strange ways, they will uninstall your SDK and you will not get money from them. Now, Firebase Performance Monitoring is a free product, so if it doesn't work for you, don't use it and you haven't wasted any money, but that was something that we really had to take into account. And as you develop a transform or a plugin, I find it very useful to use the Gradle wrapper with the -t argument. What that does is it will look for all of your source files and recompile them whenever they change. So I don't have to go through the process of saving a file, then running Gradle, install, then building my app. This is like a shortcut that made Gradle development or plugin development very, very easy for me. So that's all I have. If you go to this URL here, the bit.ly URL, that's a sample project where you can build it, run the sample app, transform its bytecode, and hopefully you'll find it helpful. Thank you very much. I'll be around for questions.